Everyone, if you're hopping on, thanks for coming back. We will get started a little bit after 10 just to give everyone a chance to hop on. But this will be part 2 of the exam prep.
About drives, fuse holders, distribution blocks, maybe some MMPs, as well as some contactors and overloads. When we're talking about overcurrent protective devices, these are your fuses and your circuit breakers, and we are going off their interrupting ratings. They don't have an SCCR rating, they have an interrupting rating. So just be mindful of that. So when we raise SCCRs, we're raising the ratings of components, and we're not raising interrupting ratings. So just want to make sure you're absolutely clear on that comment. So once again, just kind of go back and review what we learned yesterday. So we determined the SCCR under SP 4.4, which designates how to determine the overall panel short circuit current rating. So number one, we determine the SCCR of each branch circuit. After we determine the SCCR of each branch, we determine the SCCR for each feeder component. Number three, we identify the interrupting rating for each overcurrent protective device. So we want to scour the panel and say, all right, what are overcurrent protective devices? What are they rated for? And then finally, the panel SCCR is the lowest value from steps 1 through 3. So just to review, if you look on the right, you'll see the feeder circuit on the top right. That might be our fusible disconnect feeding a power distribution block. And then eventually going down to our branch circuits, tend to some motors or heaters or whatever those loads happen to be in this case.
Hey, Matt, I don't see your screen changing. I am not too sure.
Oh, no. Oh, okay. Shoot. Hang on a second. Just noticed that. All right, let me know if it's changing. Is it changing?
Yeah, you're good now.
Okay, I guess I got stuck.
And then we have a question too in the chat
Sure.
box. So somebody asked, when do you have to take into consideration the high fault rating? Is it specifically used to raise the SCCR rating of a panel?
You take into consideration of the high fault rating if you want to, quite frankly. I mean, if you want to get a higher SCCR rating in your panel, then you would have to use that high fault rating. So if in my example yesterday, where I had a contactor that was there and it had a standard rating of 5,000 amps, if I want to get that over 5,000 amps, I would have had to use another device in there. I had to use a Class J fuse, I believe in that case, a 20 amp Class J, and that would get a higher rating. So you don't have to use it, but what it does is it helps raise the overall rating of your panel. Because if you don't do that, and that contactor remains at 5,000 amps, and that's going to be your rating of your panel is 5,000 amps. So you don't have to, but the point today is most of the time, 5,000 amps is not going to cut it for industrial control panels. At the end of this presentation, I'll show you some new stuff in the NEC that came up in 2017. We're not there yet in Pennsylvania, but for people in this on this call shipping out of state and in other parts of the country, you're certainly going to want to understand that how NEC works. So when labeling panels. Okay. So hopefully the screen is changing. Can you see it okay?
Yeah, looks good.
All right. So that was the slide we talk about with components that are on there when we talk about drives and power distribution blocks and how they are component-based items. And then obviously at the bottom right are interrupting ratings of our fuses and our circuit breakers. So once again, you cannot raise those ratings of the interrupting ratings. However, we are talking about short circuit current ratings, and those are components within a panel. So just to get that a gentleman's, his remark, like I said, if you want to keep a low rating, you're more than welcome to. However, it might not suffice when you go to install it. So once again, just to recap, so now you can see the screen on the top right, you have your feeder circuit that's coming down into my branch circuits. So to kind of go over those rules again, determine the SCCR of each branch circuit, determine the SCCR of each feeder component, identify the interrupting rating for each overcurrent protective device, and then finally, the panel SCCR's lowest value. So in that case, we're using a standard rating for that contactor. You would have possibly a very low rating in this particular panel. It might only be 5,000 amps and even possibly less than that. All right, so I think we're just about caught up now. So when we're looking at this, so if we determine the SCCR of each branch circuit, we want to identify component SCCRs of each branch circuit device. And then we want to determine if the branch component SCCR can be raised using feeder components. To get back to what the gentleman mentioned, if we can get to the higher ratings using feeder devices, that might be something you need to satisfy a customer's needs. So when we look at the high faults, all right, so we're jumping right into that portion of it. short circuit current ratings of individual power circuit components. A high fault short circuit current rating for a motor controller, an overload relay, or a combination motor controller as specified in SB 4.2.2 shall only be used as a short circuit current rating of the component when the specified branch circuit protection device is provided. So what that means is if I have a high short circuit current rating on my contactor and it is specified that it must be used with a 20 amp class J, or it must be used with a particular circuit breaker, that's what has to be used, except under these 4 conditions. Exception number 1, a fuse with equal to or less than peak let through current can be substituted. So if I have a fuse already picked out, already designed in by the component manufacturer, so if they say I can use a class RK1 fuse, or I can use any fuse, I can now choose a fuse with less peak through and let through current, and I could substitute it just fine to meet that rating, to get that component high fault rating. If the panel is marked according to SB 5.1.2, the specified branch circuit protection can be provided in the field. So now I don't necessarily have to put it in the panel itself, but I do have to make sure that I mark my panel properly, and I say that on the outside that this overcurrent protective device feeding this branch must be a particular device. The next exception is a current limiting breaker with equal to or less than peak let through, and I2T can be substituted for the specified breaker as per the SCCR if the specified breaker is current limiting. So what that says in layman's terms, if I have a component and it's been tested with a current limiting breaker to get the high fault rating, I can replace it with another current limiting breaker as long as it meets that criteria. So I can replace a current limiting breaker with another current limiting breaker. That is okay. Finally, on exception number 4, a current limiting fuse is permitted to be substituted for a non-current limiting overcurrent protective device, providing the interrupt rating is equal to or greater than the specified overcurrent protective device. So in this case, if I have if the device out there, which is my contactor, and they specify a breaker ahead of it to meet its high fault current rating, I can replace that breaker with a current limiting. I could not put in a current limiting breaker. That is a change. So I just want to make sure you're aware that if I do have a component out there that has a standard breaker, I can then put in a current limiting fuse that has the same interrupting ratings, and it'll meet the standard for the high fault condition. So those are 4 cases in which I can get a high fault current rating, because part of what we're doing today is to teach you guys as well, hey, how do we do this? Because most components out there, if you're just getting them off the shelf, and if you look at the table, SB 4.1, they're going to give you the default ratings, and those default ratings are pretty low. So you really want to look at your SCCR ratings. You really want to look and say, hey, is there a high fault rating available for this component? And what do I have to do to meet that high fault rating? Because quite frankly, a high fault rating doesn't necessarily mean 65,000 amps or 100,000 amps. It could just mean you're going from 5 to 14,000 amps or 5 to 25,000 amps. So a high fault rating is just a higher fault rating than the standard fault rating that they tested with. So just know that it can change, and I have a couple of examples coming up later in this presentation when I see multiple high fault ratings within a particular component. All right, any questions? Okay. So once again, important rules applying current limiting devices. A current limiting breaker or fuse cannot be used to raise the interrupting rating of a downstream overcurrent protective device or the SCCR of a combination motor controller. So just know that you can never raise the ratings, I can't say it enough, of an overcurrent protective device. So if I have a breaker downstream that's 14 KA, I'm never going to get more of a rating out of there than 14 KA. The same with a combination motor controller. If it's a type E or F combination motor controller, I cannot raise that SCCR rating of that combination motor controller. So be aware of that. 2, a current limiting breaker or fuse cannot be used to raise the SCCR of a component in the feeder. So we've talked about raising the ratings of a component in the branch, but when I have a component in the feeder, so if I have a power distribution block, it has to be rated with that feeding device. So if I want to get a high fault current rating out of there, I have to choose it adequately to use with that particular breaker or fusible switch or fuse that's there. So if I have a power distribution block that's normally rated only at 10 KA, but you know what? If I put a fusible switch in here with Class J fuses, I may be able to get up to 100 kA. I need to know that. What I can't do is it has to be a listed on the device itself. It just can't be used by the method of looking at the let-through currents. All right, so that's in a feeder. Finally, number 3, a branch circuit, current limiting breaker, or fuse cannot be used to raise the SCCR of a branch circuit component. So what that means is, once again, as I stated yesterday, if I have a component in a branch, I have a contactor, I cannot use, unless it's been tested with the device just ahead of it, the overcurrent protective device for the branch, I cannot use that device to raise the rating of it. So what that means is if I have a contactor, maybe it's some obscure contactor that, hasn't been tested that well, and it's 5,000 amps, and I'm putting a, some Class CC fuses in front of there. Those Class CC fuses are very good current limiting devices. They won't let, that much fault current get through for sure when it does see a short, but I can't use them to raise that SCCR rating of that branch circuit component. I have to use the feeder circuit component, the feeder circuit overcurrent device. So just be aware of that as well. And then finally, utilize current limiting fuses in the feeder to increase the branch component SCCR. So that's what we've been talking about. And I'm just trying to hammer it home, guys, and make sure you're aware of that. All right, so now we're going to go through some examples, and these are just simplified. So excuse my drawings on here, because they're a little bit simplified, because I just want to make sure that it's clear as can be when we're looking at overcurrent devices, when we're looking at components, what their SCCR rating. So we've pretty much already gone through this little example here, and we've already kind of determined, we went to the charts, we went to look at what their SCCR ratings are. So as we go through each branch on here, we're going to break this particular panel down to come up with an SCCR rating of this panel. And once we come up with that, then we can say, all right, what can we do to possibly raise the rating of that panel if we need to? So if we look at this particular panel, we go branch by branch, and I wish this was in a room because I'd ask you right now. This is going to be simpler and simpler as we go on. But if we look at the branch, the first thing we have to do is to make sure that we have, we look at our overcurrent devices and we're looking at the branch itself. We're looking at what is in that particular branch. So if we've got in this particular case, we've got, I saw all the notes coming through. I'm trying to talk as loud as I can into my mic. Hopefully you guys can all hear me. If there's an issue, just let me know, Nicole, because I got my microphone kind of as close to my mouth as I can. So hopefully it's coming through just great. So when we look at,
sounds better.
Awesome. Yeah. So when I look at this particular item, we've got basically a contactor and an overload. They have a 65 kA rating on them by themselves. We got Class CC fuses in front of these things. And as I said before, we cannot use the rating of that branch to raise, of the overcurrent device in a branch, to raise the rating of those contactor and overload. So in this particular case, our SCCR for that branch is going to be 65 kA. That's what the rating is of that contactor and overload. That's the rating of that particular branch. As we go through this next branch, I'm not sure why we put line reactors in here, because it's kind of funny because there's no drive. It's just a contactor and overload again. But I guess the point that is line reactors are not taken into consideration when you're looking at SCCR ratings. So when we look at this particular example, again, we've got a 65 kA device, contactor and overload, a 200 amp Class J in this particular case. But once again, we cannot use that branch to raise the ratings of that. So in this case, again, our SCCR is going to be 65 kA. As we go through the next branch, we'll look at a drive being fed by Class CC fuses, going to a power distribution block, eventually going down to a couple of contactors feeding some motors. So in this case, when we look at what those contactors are rated at, they are rated at 5,000 amps. So when we look at the SCCR of this particular branch, once again, we can't use those branch overcurrent devices. So in this particular case, it's 5 kA. Maybe in this particular case, they were not tested. We don't know if they've been tested with that Class CC fuse. So if you look at the ratings and they haven't had any kind of combination tested ratings with them, you're going to have a 5 kA rating on those particular contactors in your panel. As we go through to branch 4, I'm just throwing out different options on here. So once again, we have a Class CC fuse feeding a power distribution block. So this power distribution block has a 100,000 amp rating, and that may have been a tested rating with the Class CC fuse. So in that case, you can get the 100,000 amp rating on there. The control relays and overload relays that are there are all listed at 65,000 amps. So once again, this is pretty easy to come up with. We'll get an SCCR rating of 65,000 amps. Finally, in branch 5. So in this branch, we just got a simple circuit breaker feeding a heating load. So in this case, we got the breaker, 18,000 amp rated breaker. And when you look at this, pretty easy to determine. It's going to be an SCCR of 18,000 amps. The next circuit is a smaller circuit breaker with a 10,000 amp rating going to another heating load. So in this particular case, once again, we're not going to get any better than that 10,000 amp rating that's on that circuit breaker. So here's where it gets a little tricky, because now we now get some a badly drawn picture of a transformer in our cabinet. So we've got a circuit breaker, which is our primary overcurrent protective device, going into our transformer, 3 kVA transformer. We're coming out of that transformer to our control circuits, right? So in this particular case, we actually have a GFCI receptacle. So we can use some of the rules that are in place for power transformers. So in this particular case, we have a 3,000 VA transformer, 480 primary, 120 volt secondary. So if we go over to that column in column 2, if we look at the minimum transformer secondary voltage of 120, we look at the amount of current that can come out of that as 1,200 amps. So this is a safe circuit, meaning that we've designed it okay. We can now use that primary overcurrent protection device to be able to handle all the faults, to be able to be rated at that rating. So in this particular case, I'm using that primary overcurrent protective device, which is that circuit breaker. It's 14,000 amps. The reason we can do that is if you look at the GFCI, that's a 2,000 amp rated device. What's going to get through that transformer is only 1,200 amps. The 1,200 amps is less than a 2,000 amp rated device on a GFCI. So because of that, we can then use that primary overcurrent protective device on that transformer, and that becomes our circuit SCCR, our branch SCCR in this particular case. So in this particular case, again, once we have another application where we have a 65 kA circuit breaker feeding another transformer. So in this case, we've got a 10,000 VA transformer, 480 primary, 240 secondary, going through another circuit breaker, and then finally going through some contactors to our motor. So when we look at this branch, we have 25,000 amp max rating right now on the control relay. But as we look at the available short circuit on the secondary there, we go to our 10 kVA row, we go across to the 240 volt column, and we look down and we say, you know what, okay, at that kVA and that voltage on the secondary, we only have 1150 amps able to get through. That 1150 amps is certainly less than the 65 or the 25 kA rating of the contactor and the 35 kA rating of the overload. So in that particular case, once again, we can go back and we can use the primary overcurrent protective device in that circuit. So we're looking at the device on the left of the transformer, that 65 kA circuit breaker, CB 8.1. That's going to dictate our SCCR rating. We can now use that primary overcurrent protective device as our protection for that circuit. All right. Any questions on this or using transformers and using the tables? Just remember, though, this is an either-or situation, so you need to make sure that you look at some of the rules for applying the transformers. In some cases, you may need to actually calculate the fault current on the secondary of a transformer. And within SB4, they do give you, the rules on how to do that. So just take a look at that and make sure you're aware of it. But this is kind of a quick way to understand, when and how you can use the primary overcurrent protective device as your branch SCCR rating. The next item is a Class CC fuses feeding a power supply. So in this particular case, we can just take the SCCR of the Class CC fuses because we don't have to take into consideration a power supply. So now we can use that Class CC fuses as our primary SCCR for that particular branch. So as we look through the panel itself, so now we went through. So we did the first portion, right? We looked at every single branch that we have in our panel. So we went branch by branch by branch. We determined what they are by branch. So if you look there, we've got 65,000 amps on one, another 65,000, a 5 kA, 65 kA, and an 18 Ka, a 10 Ka, 14 Ka, 65 Ka, 200 K. So we're all over the place with our ratings if you look in this panel, right? So if you look at this panel right now, when you look at the step 4, you take the lowest rating of all these, and that's my panel SCCR. So right now, when I look at my lowest rating right now of these branch devices, we're going to have a panel SCCR, of 5 Ka. So we take the lowest device in there, lowest SCCR, and right now that's it. So I'm telling you right now, if you have a enclosed industrial panel, and it's fed by a 200, if it's got a 250 amp circuit breaker or a 250 amp fuses, you're probably going to have more than 5,000 amps available to that. When you look at industrial facilities, Eaton did a study a few years ago that when you look at what current comes into an industrial facility, most of the time on the secondary of the main transformer coming into the facility, you'll see 65,000 amps. As it goes through the facility and as you have more and more impedance in the wiring and those types of things, you'll drop that fault current. So now, but what they found is that at a lot of industrial plants, once it gets to the actual industrial control panel, you'll see values, around 35,000 amps. So just to let you know out there, if you can design your systems to handle 65 Ka, you're probably going to be able to do 75 to 80% of all applications out there with no problems. It's very certainly in most cases, like I said, at the secondary of the terminals of that transformer, you'll see 65, but as you get down through 35 can be more common. So even in many cases, if you just design for 35 or 45, you can get to those ratings. It seems to be that most overcurrent protected devices, though, when we're talking about breakers and those kind of devices, are all going to try to get to the 65 Ka rating. So obviously, I encourage it. If you can design a 65 Ka panel, it's going to help you in many, many, many applications to meet the standards. All right. So as we go through this panel, we're going to see what happens if we take that feeder device and we say, you know what, we're going to change that feeder that's in there, that particular overcurrent protected device. So instead of just having a molded case circuit breaker in there, we're now going to put in 350 amp class J fuses. So what's going to happen when we all of a sudden say, you know what, we got to redesign this a little bit. Let's see what we could do to possibly raise the rating of this thing by putting in a different overcurrent protected device in our feeder circuit. So right now, hopefully you remember this a little bit from yesterday, but we're going to go through it again. When we look at the ratings and the let-through currents of the fuses, we need to look at the tables in table SB 4.2. All right. So when we look at those tables, and in this particular case, we're going to look at the 100,000 amp column. All right. We're going to try to get the let-through current on a 350 amp class J fuse on the 100,000 amp column. So if we go to that table SB 4.2, we go to the 350 amp range for a class J fuse. We go over to the 100,000 amp column, and we can find the peak let through current. So in this particular case, we're going to have 29,000 amps that's going to be able to get through that fuse. So if we can design our components downstream to be able to handle less than that, there's a chance we can raise those ratings of those devices. So let's take a look at those devices branch by branch and see what we can do to possibly raise this rating up beyond the 5K rating it has right now. So if we look at the first device, first branch that we have out there, once again, we have a 65,000 amp system. So in this particular case, we have our control relays or our contactors that are rated at 65,000 amps. They are certainly over those ratings are certainly over the let through that could potentially come through from that class J fuse. So in this particular case, we can take this branch and we can increase this up to 100,000 amps. So just keep in mind, we're not going up to that 200,000 amps of the class CC. We're going up to that 100,000 amp rating from column SB 4.2 from that table. So we're able to raise the rating of this particular branch all the way up to 100,000 amps using those let through currents. Okay. If we look at the next example, all right, we have an original SCCR of 65 Ka. If we've got a class J fuse in there, once again, we can now all of a sudden, once again, raise that as well up to 100 Ka rating. So we can go all the way from 65 up to 100 Ka, and we didn't change anything at all in that branch. As you move down to branch number 3, we have the 200K rating of the class CC, feeding a VFD, feeding a power distribution block that's rated at 30 KA. And then we have some other contactors and overloads on there that are rated at 65,000 amps. So original SCCR of this particular branch was 30,000. As we look, obviously the feeder circuit's letting through less than 30,000. So once again, we could take this whole circuit that was rated at 30,000, and we can get it over that maybe that 65K threshold that we really want to get beyond. So once again, we're able to raise the rating using the rules set in place for the feeder circuit overcurrent device. So in this particular case, again, we have class CC fuses feeding a power distribution block that's 30 KA on our contactors and overloads. One of them are actually overloads have 65 KA ratings on them. The overall SCCR for that branch was 30 KA. Once again, we're going to increase that whole branch up to 100 KA rating. So very good thing to be able to do this kind of stuff, guys. So in this particular case, we've got a 65 KA rating on CB5. When we looked at that SCCR rating, we've got 65,000 amps. So if I was in a room with you guys and say, hey, can we raise this rating? Is that overcurrent device and our feeder going to be able to raise this rating? Hopefully everyone out there in the audience is saying, no, can't raise that rating. Can't raise that rating. That's an overcurrent protected device. So nope, our rating still stays 65,000 amps. So once again, you cannot raise a rating of an overcurrent protective device. Can't raise a rating of that circuit breaker. So you're going to be, it's a fine rating. 65 is a good rating. So we'll leave it where it is. Same thing with this one. Can we raise that rating? Nope. Once again, it's a 65 KA, but we still can't raise a rating of that 2-pole breaker. So can't use the rules to do that. And now we have a 65,000 amp rating on that branch as well. And then finally, as we go down through this circuit, we have this is where it might get a little tricky for you guys, because once again, we're using the rules of the transformer rules. So our initial SCCR was 65,000 amps. You look at this component that's downstream, it's a 2,000 amp. It says it's 2,000 amps. Why can't I raise that rating? We're trying. Well, because we still can't raise the rating of that breaker CB7, right? That CB7 is always going to be 65,000 amps. We're not going to be able to raise that rating using the rules. So in this case, once again, we're going to have a 65,000 amp rating. So it's not always just the components that you want to try to raise. You also got to look at your overcurrent devices as well, right? What are you picking and choosing? Once again, we go back to our other transformer device, and hopefully you guys learned from the last example. Sorry, I'm hammering this home, but this is a common example, a common problem I see out there, where we have overcurrent protective devices that are out there and people think they can raise them. In the commercial world, guys, you'll see this sometimes. It's not really raising the ratings, but you'll have things out there called series ratings. Industrial control panels cannot be series rated. When you're in a commercial environment and I have a panel board, I can potentially series rate that. What that means is I can put a fuse ahead of it and say, you know what, my fuse is going to protect that panel board. So I can get maybe a higher rating out of there, but it has to be a tested application or it has to be signed off by a professional engineer. In the industrial control world, guys, there's no such thing as a series rating. You can't raise that overcurrent protective device. So once again, in this particular case, we're going to have an SCCR rating of 65 KA. And then finally, no need to raise that rating. We already got a 200,000 amp rating on that device. So we're going to leave that where it is. And then now when we look at the overall panel rating, we were able to go and raise the ratings of all these devices up to the rating that we need to maybe satisfy the customer's responsibilities. So we can get a 65K out of our power distribution block. We've got 65K minimum throughout this panel. So now all of a sudden we can go ahead and rate that overall panel SCCR at 65Ka by just paying attention to what devices that we use and what devices we use on our feeder circuit. And can we use those devices to raise the ratings of components downstream? So it's super important, guys. I know I'm hammering it home, but hopefully you understand it. So when we look at fuse substitution, remember that for high fault short circuit current, you are permitted to substitute an equal or more current limiting fuse of the same or smaller amp rating. So if you do have a situation where I've got maybe an RK1, I can replace that with a class J if it's designed to do that. So we can do that as long as the it's a more current limiting fuse going in its place. So you determine how current limiting a fuse is by looking at its peak let through current, the I sub P and I squared T from table S4.2. So in case you guys have never heard of what I squared T is, basically that's the destructive energy that can come through. It's the amount of current squared times the amount of time it takes to open that up. So that's basically a destructive energy that can get through an overcurrent protective device. So if we look at that, one thing I want to make sure you're aware of is that if you're going to do this, if you're going to look at current limiting fuses to help to raise the ratings of components, you must look at SB 4.2. What you can't do is you can't look at our let through tables. So Busman has let through tables that we publish. Fuse manufacturers that have current limiting fuses have let through currents that we publish. You can't use them though, guys. I want to make sure you understand that when you're using let through currents, you have to look at the table SB 4.2. You can't use it. You can't look at the manufacturer's website. You can't look at the manufacturer's let through current. You have to use the values that UL publishes, and they are basically some umbrella ratings and for all Class J fuses. So in this particular example, the reason we can't is because our devices may be more current, may be more or less current limiting than what's on the UL site. So we want to make sure that we're using their official let through currents as published in SB 4.2. So just be aware that you need to do that. So as I stated, you must use values from SB 4.2. So when we look at substituting fuses in the field, if there is a component that was marked for use with, let's say, an RK1. So if I look at the bottom and I say, can I substitute 100 amp Class J for 100 amp RK1? Maybe I have an old contactor, an NEMA contactor, and they tested that thing to get a combination to get a high fault rating with 100 amp RK1. Can I use a Class J fuse? Well, in this particular case, if I go up at the I sub P and I look at the I sub P at 100 Ka and I look at the I squared T at 100 Ka, the 100 amp Class J, which is the top fuse on there, has a 14 Ka rating on there, and that's obviously better than a 16 Ka. It's going to let through less peak current of the RK1. So in this particular case, yes, I can substitute a Class J for an RK1. If I go down and I also look at the Class T fuse, can I take a Class T fuse and substitute it for an RK1? Well, once again, Class T and Class J have very similar ratings. So when we look at the I sub P and we look at the peak let through as well as the I squared T, in both cases, once again, the Class T fuse does a better job than the RK1 fuse. So in this particular case, once again, I can now replace that class RK1 with a Class T. Let's look at the opposite case. We have a contactor that's specified with a Class J fuse. I got a Class J out there. That's rated at 14,000 amps. For peak let through, can I go the opposite way? Can I put an RK1 fuse in there? Obviously, the answer is no, right? The answer is no, because now all of a sudden that rating is not the same or less. It's now higher. So we want to make sure that we are at least substituting in like kind fuses or better. So the last example, can I replace a Class J with a Class T? So in this case now, if I look at it, yep, you know what? They have the same ratings by SB 4.2. They have the same let through. They have the same I squared T. So once again, I can now substitute that fuse, a Class T for a Class J and vice versa, because in this particular case, they have the same exact ratings. So they can be substituted to build your panel and to meet that rating for that component. Any questions so far? Okay. So I did label this as part. Yep.
Oh, sorry. If we call Busman fuses on the application itself, can we at that particular point use your tables or always have to go by 4.1?
If the manufacturer calls for a certain fuse, then you'll need to use the manufacturer's recommendations for that. So, because many times when you're looking at drives and other devices, they may spell out an actual fuse to be used. So you do want to look at the manufacturer's recommendations, especially on drives and those kinds of things. It's rare that you'll see a particular brand spelled out unless you're talking about breakers for the most part, because when you're talking in the breaker world, they're gonna spell out a particular breaker to be used ahead of it, because not all breakers are made the same, and there's no real umbrella ratings that you would have in the fuse world. So there are manufacturers of drives and other particular components that will spell out because maybe they just wanted to get the testing done. You know, they went through UL test and said, you know what, I got the ratings and I use this particular fuse, so I've tested with this, so that has to be used. So look at the manufacturer's recommendations in that case of the component. All right, so we're looking at branch and feeder spacing. This is one thing I just want to make sure you're aware of as well. So we look at branch circuits versus feeder circuits. So it's very important to understand, because another common issue that I see out in the field is using power distribution blocks and power distribution terminal blocks where they're not supposed to be used. So when we look at a branch rated device, there's certain spacing that has to be required when you're talking between, you know, uninsulated live parts and insulated live parts in walls in a metal enclosure. So under table 10.1 of UL508A, you'll see these ratings in there. So they're very important to understand. So in this particular case, I may have, you know, in a particular 480 volt system that I highlighted in red here, you'll have a spacing requirement that is required when you're putting together devices in branch circuits. This is particularly important when we're talking about feeder circuits. So one of the common things that I see out there is where people put in the wrong device for a power distribution block. When we're talking about feeder circuits, you need a particular distance again, and it's much greater than what's in a branch circuit. So if I go back to the branch circuit, I'll see that I maybe need 3/8 inch or a 1/2 inch at most over surface to be able to be used in a branch circuit. When I go to a feeder circuit, I now need to get much more clearance out of this thing, right? It's typically going to carry much more current. It's going to multiple pieces of equipment. So now in this case, I've got, you know, 1 inch through air and 2 inches over surface in this case. So just be aware when we're looking at branch rated devices, there's a difference than feeder branch or feeder devices. So when we talk about UL 1953 power distribution blocks, which I'm going to show, they are a true UL listed device. So as I go and I look at some devices that are out there. So if you guys have never been on, have ever looked at table SA, you can now go onto the UL's website to see this. They list all the different components that are out there and the UL standards for them and whether they're recognized or not. So under UL 1059, so if you look at the one I highlighted up top, UL 1059, when I give you an example or show you one of these coming up soon, you'll say, geez, I've used that before. I've used that before. Well, they're not designed to be used in a feeder system. Typically, these blocks do not have the spacing requirements to be used in a feeder application. So it's very important to understand which power distribution blocks you're using. If I look at the bottom of that, and you'll see to the right of this, that you see the SCCR2, right? So that's recognized terminal blocks. That's basically what this falls under. So there's a lot of recognized blocks out there. When you look at the category control numbers, anytime you see a 2 at the end of it, you'll see that they're pretty much going to be a recognized system. So for instance, when we look at, you know, below this, you'll see the ZMVV, and then you'll see the QPQS. You know, they don't have the 2 after them, and those are a lot of listed devices. So you'll see that we've got listed power distribution blocks at the bottom of this. We have listed pressure wire connectors. So these are listed devices. When we talk about recognized terminal blocks, and we look at the SCCR2, if we go to the next slide, you'll see that when you look at terminal blocks, and what that means is you have to apply this within a certain way. So within a recognized system, you know, there are certain conditions that have to be met in order to use those recognized parts. So in this particular case with these terminal blocks, these are TB200 series terminal blocks that are out there. You'll see it has a wire range size, and it must be copper wire type, and it might have, you know, some voltage ratings depending on what type it is. So it might only be like one blocker for one application, and you'll see that the user guide up there lists the user guide sections, and in this case, it's B, C, D. Well, when you look at that in great detail, you'll see that, geez, under Product IQ on UL's website, there's a lot of different applications that terminal block can be used on. And depending on those applications, that's what it's recognized for. So if I'm using it in commercial appliances, there's one set of criteria for that, how much spacing I need to use. If I use it for industrial general, there's another set of spacings I have to use. And then obviously if there's limited ratings, industrial limited ratings under D, there's a certain spacing I have to use. So just know that when we're talking about recognized products, there are certain criteria behind those things that you have to know compared to a listed product. So when I look at a listed product, I look at some of the power distribution blocks and other devices we have out there. So our UL 1953 blocks, right? You can see right away all the spacing that is on these things. That's a true power distribution block. Block falls under 1953. It's listed as a power distribution block. It has the spacing that is provided to be able to be in a feeder circuit. So it's very important to understand when you're using feeder circuits, you have to meet that minimum spacing. The finger touch safe one on the left gets all the spacing because of all the plastics it's encapsulated with and between the live parts. So that's a single pole unit on the left. And when you mount and three of them together, snap three of them together, obviously you get a 3-pole unit, and you clearly have enough space then over the surface and through the air to make sure they can be used in a feeder application. The guys on the right are UL 1059 terminal blocks, right? A lot of times you call them power terminal blocks, but a lot of people call them power distribution blocks. They're not UL 1953 power distribution blocks. So I've seen this a lot where they use a 1059 block in a feeder circuit. And I've seen it in places where it's caused a problem, quite frankly. I've been in a situation where they were too close, had too much power. They ended up arcing between these, and it caused an issue. So just know, and it was investigated. That's the bigger issue, right? Because now all of a sudden somebody got hurt. Unfortunately, they did some investigation. They realized that, you know what, a 1059 block was used where a feeder was designed for. It didn't meet the spacing criteria, and now there's an issue. So just be very aware of that when you're picking out your blocks. Make sure that you know, get a listed power distribution block and it meets the feeder spacing requirements. Very important. When we look at power distribution blocks protected by an overcurrent protective device. So about, I don't know, 15, 20 minutes ago, I told you when you're looking at your devices, when you're looking at your listed devices, or you're looking at the SCCR ratings of your devices, they can change depending on the overcurrent device feeding those devices. So hopefully this makes sense, but on our particular power distribution block, our PDB 323, we have multiple short circuit current ratings for this particular block. And it's not uncommon to see this in the power distribution block world for sure. And this can happen with other devices as well. Certainly we saw it yesterday with the contactor where I have one rating with a fuse and one rating with a circuit breaker. Well, it gets even more granular in some cases, especially this particular case. So now if I'm looking at my ratings on here, you know, what are they? So if I look at the top row, okay, so on my line side, I've got 350 to a number 4. On the load side, I've got a number 4 to a number 6. As long as I don't have smaller cables in that, wires in that, I can get a 65,000 amp rating out of that power distribution block by using those two breakers, those two specific breakers on there with a 250 amp max rating on those. So if I stick to those rules, they've been tested with that breaker, I can get a 65K rating out of that power distribution block. If I go down and I say, you know what, I need to put number 8s on the load side of this thing. Geez, you know what? Okay, well, I can still get a 42,000 amp rating out of this thing. All of a sudden now I lost my 65K rating on this. I can't rate it that high. It's by the distribution block manufacturer. That's what it's been tested to safely handle. Once again, it's with those two same breakers, but now all of a sudden we've got number 8s on there, so we're not going to be able to handle as much fault current. And the reason for that is, you know, when we test them, maybe they pull away from the terminals, not necessarily going to explode or cause maybe an arcing. Well, they could potentially cause an arcing issue, because if they do pull away from the terminals or do something else, then it could obviously cause a situation where we're arcing and causing, you know, a shock hazard for sure. Once again, I want to go smaller. I want to put number 10s on this. All of a sudden now I've dropped all the way to 14 Ka. So I go all the way from 65 Ka to 14 Ka. I'm putting in the same breakers. Now all of a sudden I could choose another 4 or 5 breakers as well if I want to, because now I'm only need a 14 Ka rating. I can now do that. So just know that if I want to get that rating, you know, I have to look at the specifics. If I want to look at a different particular breaker, so once again, you drop even below that, we can get different ratings with different breakers. And as you go to the bottom, now we look at fuse classes and max amp rating with fuses. Same deal. We have a 350 to number 4 on the line side, but on the load side, what do we have? If we got number 4 to number 8s, we can still get a pretty high rating out of this. So if I want to go down into a number 8 with a breaker, the best I'm going to do is 42,000 amps, right? But if I all of a sudden want to get to a number 8 and I can put Class J fuses in there, I can go all the way up to a 400 amp Class J fuse. If you look at that column for Class J, you'll see 400 below there. if I scroll all the way to the right, my SCCR is going to be 200,000 amps for that application. If I say, you know what, I don't have Class J, I want to put in an RK1 fuse, that's what I have. I can now say, okay, with an RK1, I can still get a 200,000 amp rating, but I can only put in 200,000. I'm sorry, I can only put in 200 amp rated fuses. So just know that we can change, that will change. When I look at maybe an RK5, I can only put up to a maximum 100 amp RK5 to get that rating in there. But as I kind of explained before, Class J and Class T are very similar in their characteristics. And if you look at SB 4.2 for the let-through curves, you'll see that, you know, all of a sudden now I can use a 400 amp Class T in there as well and get that 200,000 amp rating. Once again, if I want to drop and now go all the way down to number 12s, the nice thing is I can actually go down to number 12s now and get a high SCCR rating with a fuse. I could not get it with the breaker above. So if I do want to put 12s in the load side of that, I can now put some Class G fuses in there if I want. I can put Class J, RK1, Class T, Class RK5 if I want, and still get a 100,000 amp rating out of there. So just know when you're looking at SCCR ratings of some components, you really got to dig deep into some of the installation and some of the instructions they have on what really you're going to get when you get to SCCR ratings. All right. Sometimes it's just not as simple as it was yesterday, where, you know, 5 kA with a fuse, you know, you know, maybe I can get, you know, 65 K with a 20 amp fuse. Well, now we're getting way more granular in this case because now we have other options, right? We now have options what can go on a secondary of this power distribution block.
Hey, Matt, there's a question in the chat.
Sure.
Someone's asking if you only see your unmarked on the power distribution block is UL1059.
If it's unmarked,
I think that's what they were trying to say. I'm not too sure.
well, if it's not only 1059, you have to see whether it's a recognized part or not. If it's you want to make sure that if it's a 1059, it's not going to be good in a feeder circuit, and you could probably use it in the branch circuit as long as you keep the minimum space requirements. And in those cases, if it's unmarked, you'll have to use the standard faults that you'll find in the tables in supplement SB. So they'll tell you I believe it's 10,000 amps in that case, but I'll have to verify that. But if it's unmarked, you'll have to then look, and obviously you want to investigate it to see. But if it doesn't have the spacing, it's pretty clear right away if there's a spacing on there. So when you're looking at that and you see there's tons of space on there, you still want to make sure it's a listed device, right? You still want to make sure that when the inspector comes, your UL guy comes, that he sees it. But otherwise, it's probably going to be a 1059 device that would have to be used in a branch application. But you still want to make sure it has that recognized component to it. All right, so just some general notes as what you find in section 29 for internal wiring. So all conductors and bus bars on your power circuit have to be copper. So make sure you're using copper connectors and copper wires in your panels. Conductor insulation is rated for the maximum voltage involved in that power circuit. So you want to make sure that it is rated for that. Conductor temperature ratings have to be rated for 90 degrees C. That's the minimum. So make sure that you are doing that. Machine tool, these are all the different types of conductors you can use as well. Machine tool wire or Class K type machine tool wires, thermoset insulated or thermoplastic insulated wire. Those are the types of wires that can be used. And then finally, when we're talking power circuit conductors, 14 gauge minimum. So make sure you're using 14 gauge minimum in your power circuits. There are some rules for control circuits. They are different, but right now we're just talking about power circuits, conductors, and what their minimums are.
Matt, we have another question.
Sure.
Someone's asking, why does the SCCR differ for number 8s?
For number 8s?
Mm-hmm.
It could be, quite frankly, when we put these through testing, we have to test all these scenarios. So that's why when we test these, you'll notice these are Eaton devices, right? Because we're Eaton, part of Eaton now. Years ago, before we were acquired by Eaton, we just tested these with fuses. So all of a sudden, we would have great ratings with our fuses. And all of a sudden, once we became part of Eaton, well, when we test, we have to test under all these criteria. So it may have just failed the test. So when we put these through the test and we because trust me, we'll try to get the best rating we can out of these things. So if you go to Busman, for example, we have a testing lab. we can test several 100,000 amps in our lab. It's pretty cool, actually. We blow stuff up there on a daily basis. Other companies come and blow stuff up there as well, and they test their devices to see what they can safely handle. So in this particular case, my gut feeling is we probably tried going as low as possible. We just couldn't get there. So once we said, all right, we can't get there, what can we get to? So, okay, we'll go to a number 8. So when we use fuses, we can obviously get to a number 12 because of the let through nature of the fuse. So all of a sudden now that fuse is going to let through much less fault current if it sees a fault current go through there. So with the current limiting nature of that fuse, that's why you're going to get higher ratings. That's why when you look at the fuse ratings that are on there, Class J and Class T are very strong current limiting fuses. They'll do a very nice job current limiting. They operate very quickly. That's why you can use higher ampacity Class Js and Class Ts in this particular case. When we look at RK1s and RK5s, those have more time delay built into them, and they're also not as good of a current limiting fuse. They're still current limiting, but not as good current limiting fuse. So that's why in those cases, we can't get to a number, 12 using, we'll have to drop the ratings of our fuses to make sure that we can, let through the fault current, the smaller amount of fault current. So a 175 amp Class J has much more current limitation than a 400 amp Class J. So that's why in that particular case, we probably got it rated to use number 12 because of the current limiting nature of it. Same thing with the RK1. 100 amp RK1 has much better current limitation than a 200 amp. It's just a smaller element in there, and we can open that thing up a lot more quickly. So that's really why, I don't have specifics, but that's really why I'm guessing, because we tried probably, and we just couldn't pass the test. So now we're just, whatever we could pass it at, that's what we listed it to.
And then it looks like we have a follow-up question to that question and then another one.
Okay.
So someone's asking, should we use the 42 or the 50 in that situation?
The 42 or 50 in that situation? I'm not sure what you mean. Oh, I see what you're saying. You can use the well, you're going to have to use, it depends on the breaker that you're using. So in this particular case, you'll see that up top, it's a JGH breaker, and on the bottom, it's actually a JGC breaker. So they are spelled out differently. So there are different overcurrent devices you have to use. So that's why it's very tricky. You have to make sure you look. So it depends on which breaker you have. So it'll be 42 if you're using a JGH or the J250H. That makes sense? There are subtle differences in those part numbers. I know it's tricky, guys, but when you look closely, you'll see that those part numbers are different.
All right, and then someone asked us, it says terminal blocks between the motor starter and the load, UL1059 type. Should they be analyzed in the SCCR calculations?
Yeah, yes.
Yes, okay.
Yep. If they're if any component in the branch has to be, any component that's in the power circuit has to be analyzed, including the terminal blocks at the bottom of your panels, guys. So just be aware that you've got terminal blocks at the bottom of your panel that are for bringing in your equipment from outside. That's in your cabinet, and you now need to take those into consideration. So just be aware those are another gotcha. So terminal blocks are a big deal, especially if you're putting in a row of dinner mount terminal blocks at the bottom of your panels. You need to take those into consideration because they are part of the power circuit. Now, if they're control terminal blocks, you don't have to worry about it. So if they're just bringing in your control wiring, that's not part of the SCCR. But if you're landing your motors to those and going into your drives, that has to be taken into consideration. So sometimes people just go right into the drives and take those out of the equation, so that way they don't have to worry about having terminal blocks at the bottom of there. All right, we're good.
You're good.
All right, so we went over this a little bit. We talked about that. Fine stranded wire, just make sure you're aware, guys, that when you're talking about stranding of wires and what they are, you have to make sure that your terminals are labeled for those types of wires and cables. So when using fine stranded wires, your terminals must be rated for fine stranded wire. That's, you want to definitely look at that, because there's cases out there where I've seen people using it, and really it's not designed to do that. So you want to take a look at your component that you have, whether it's a contactor or fusible switch or whatever it happens to be, you want to make sure that those terminals on there are rated to be able to handle that particular wire, whether it's stranded, solid, or fine stranded wire. That seems to be the one that's most common that is a hiccup. Ferrules used for factory wiring only. I just want to make sure that stranded wires using ferrules become solid conductors. So in some cases, if you want to use a fine stranded, you then can put in a ferrule and you can use it. But just know that by itself, you can't put a fine stranded in there. But once you put a ferrule on it, as long as it's not from the field, right? You can't use ferrules from, it's only for internal wiring only. We cannot use those for external going out to the field. So field wiring, it's 125% of the load, 14 gauge minimum, cannot use ferrules. Once again, field wire terminals must be rated for the wire size. Internal wiring, you can use 100% of the load. Once again, number 14 minimum, must be copper. You can use ferrules, and the terminals, once again, must be rated for the wire size. So I'm going to touch on disconnect switches a little bit right now. So when we talk about the disconnect switches and what types that are out there and how you size them, I'm not going to go into great detail on how to size them, but just know that in section 30, it covers disconnect switches. So typically you'll see in there that it's 125% of the circuit FLA for circuit breakers or fuse switches. So that's where you want to size them at. When we're talking about non-fuse switches, molded case switches, pullouts, non-motor loads, you can size them at 100 amps, I'm sorry, 100%. We're talking about 115% for motor disconnects, and it must be capable of breaking locked rotor currents. All right. So general rule of thumb, 125% for circuit breakers and switches, and 100% for non-fused and for non-motor loads. When we're talking about the locations, you know, a disconnect switch must be provided for each supply. So if you have a supply coming into your panel, you must have a disconnect switch for that supply. If not, then it must be marked per 60.1. So when you look at 30.3, it says, hey, you got a supply disconnect, but if you don't, there's an exception, but you have to label it that way and say, hey, you know what? It has to be labeled that is supplied by, you know, disconnect is supplied elsewhere, you know, by you know, another means, but it has to clearly be labeled that way. So if for some reason you have multiple disconnects within your panel or multiple supplies, maybe you've got, you know, control and power coming in there. You want to make sure that if you got multiple disconnects, they are grouped together in your panel. If they're not grouped together in your panel, once again, there's an exception. You can make a note out there to say, you know what, I haven't, you know, it's not together, but here's where it is. So you have to make sure that you either put them together or mark it that way so that whoever is working in that panel, they know how to shut that power off properly and be able to work safely.
There's another question in the chat.
Okay.
Okay, I'm probably gonna butcher how to say this, but it says, can you clarify the ferrules on the field wiring example? Am I not permitted to use the ferrules on terminal blocks feeding a motor circuit from inside my control cabinet?
If it's coming from the field, you can't go into that block, meaning that if I'm coming from the field directly into that terminal block, can't use ferrules there. But if you're inside the cabinet, meaning that it's wiring from point to point inside that cabinet, you could put ferrules in that cabinet. That makes sense? So when we are looking at non-fused disconnects, and there's two types that are out there, I want to make sure you're aware of UL98 versus UL508. So UL98 disconnects can be used in feeder circuits as well as branch circuits. They have the spacings required for feeder circuits, and any device that can be used in a feeder circuit can be used in a branch circuit. So just be aware of that, because they're typically more heavy duty than what you would see in a branch. So a UL508A disconnect can be branch or at the motor disconnects only, and must be protected by a branch overcurrent protective device. So this is a common misapplication as well. A lot of people will take a UL508 disconnect and they will put it inside of their panel as their primary disconnect in that panel, and that may go down into a power distribution block, and that's a no-no. So you can't use it in your panel as the primary disconnect switch. It must be a UL98 disconnect, must be labeled and listed that way. So just when you're looking at it, if you look at it and it doesn't have some sizable spacings, you don't see, like if you look on the panel on the left, or if you look at the disconnect on the left, you'll see that it has more spacing per phase to make sure it meets the feeder circuit rules, right? So when we're looking at the UL508, clearly it does not. We use these a lot at the motor disconnects where maybe you just got an isolated motor, but you know what? Upstream, I have branch devices. I have other overcurrent protection in there. It's not my primary UL98 disconnect, but it can be used. When we're looking at bus bar systems, so if you look in table SB 4.1, which has all the the standard ratings, so it's a standard rating for bus bar, for your power distribution blocks, for anything that doesn't have any kind of rating on it, your standard ratings would apply. If you don't want those apply, because quite frankly, a bus bar system, the standard rating is 10,000 amps. Obviously, you've got a pretty sizable bus bar, it's going to see more than 10,000 amps. So you can get higher ratings out of the bus bar systems now. It used to be that they had previously there was only fault ratings for motor controllers. So if these were on bus bars that maybe were on motor control applications and those kind of things, they were rated. But now you can get higher SCCR ratings from the manufacturer. So when you look at to get a higher rating under SB 4.2.4, it says use of a bus bar system that complies with the standard for industrial control equipment, UL508, with the short circuit current rating marked in the component or on the instructions provided with the component and installed according to the installation's instructions provided. So what that means is if I'm buying a bus bar system from somebody and they have a 65,000 amp rating on there and they tell you how to do it, you can use those ratings now. You can put a bus bar system in using what they tell you and what is acceptable and what is rated and marked on their component, on the installation instructions, etc. If you don't have that and you want to roll your own, maybe make your own bus bar system, you've done it for a while, UL has criteria for that. So when you look at Appendix D within this, you'll see the criteria for spacing and marking when you want to get a higher fault current rating out of this thing. So just know that there's basically two ways to do it. Comes from the manufacturer that way and it's marked that way, or it comes you do it yourself and you're kind of rolling it based on Appendix D and in the UL508A standard SB. Right. So I'm going back to supplemental protection because I always like to hit this a couple of times as well. So just be aware that I like to show other types of supplemental protectors as well. So when we look at a supplemental protector, when it's a breaker, for instance, that top right item, guys, is not a branch rated device. So just be aware, you always want a UL489. A 1077 device does not meet the criteria for branch protection. When we're looking at fuses, same deal with fuses. If it's not a class of fuse, it's not going to be rated that way. So our supplemental fuses, yep, we use them in control panels. Sometimes we'll put them in a secondary control transformers, that kind of a thing. But the biggie are manual motor controllers. So just know that in most cases, manual motor controllers are considered supplemental devices, right? They're there for some overload protection. Maybe they do some instantaneous protection, but they're not designed as a branch rated device. So I see, like I saw a quick question, I think, that popped up and went away. When can you use a supplemental device? Typically, a supplemental device is there to protect a piece of equipment within the panel. So if it's in my control circuit and I've got a branch device ahead of it, let's say I've got a 15 amp branch, but you know what? I truly just want to protect a particular device in a panel. Maybe it's a little controller, or maybe it's a little PLC or something like that. I can use a supplemental protector. I'm not trying to protect that whole branch. I'm now just protecting that device. So a lot of times I'll get, like in supplemental fuses, for example, if you guys have a Fluke multimeter, you'll see our supplemental fuses inside of a Fluke multimeter in many cases. So that fuse is in there as a supplemental protection, just in case you do something you're not supposed to, and you put, maybe you touch the wrong thing with your meter. Hopefully that fuse is going to pick it up okay, and then not short things out. So, and not cause any damage or hurt people. So you'll see those type of applications. You'll put, I might see them in other applications for inside of a inside of a component. Maybe there's a meter manufacturer who inside of his meter itself, he's got supplemental fuses in there just to protect it as well. So those are typical applications you'll see supplemental protection. So I kind of went over it. They do resemble circuit breakers, so just know they are different. You can see these though sometimes in your control circuits, but not to be used as branch protection. So we'll go over a little bit of sizing circuit protection. So I'm not going to delve into it too much, but just want to give you a general idea where to find it and some of the things in there, because, you know, we don't have it. We have, how many on time? We got about 50 minutes to go. So if we look at, you know, what we can do for sizing branch circuit overcurrent protection, I'm going to give a couple of examples on how to do it for motors and for some feeder applications. So in this particular case, we've got our motor branch circuit, short circuit and ground fault protection. We've got our motor controller. We've got our motor overload protection. So how do we size these things? How do we size our fuse? How do we size our circuit breaker in these cases? So if we look at these devices and we go to the chart, so it happens to be table 31.3 in this particular case, it'll tell you, hey, what am I using in this case? Am I using a time delay fuse? Am I using a non-time delay fuse? Am I using an inverse time circuit breaker? Am I using a instantaneous trip circuit breaker? You know, what is it? So if I go to the correct row, so let's say in this case, very, very, very common, the third row down where it says dual element fuse time delay, but it says except class CC. So we see dual element fuse time delay except class CC. You go across, and your nominal rating of a motor branch circuit protected device is 175% of the full load amps. So that's where we want to size it. So when we look at, you know, class CC, now all of a sudden you'll see dual element fuse time delay. It says class CC dual element fuse time delay. So in that case, we can go up to 300% because a class CC fuse in general is very fast acting, and you have possibly a potential for it to maybe give you a nuisance trip. They will let you go a little bit higher in that particular case. And when you have a non-time delay fuse, which I very, very rarely use in a motor application, you really want to use a dual element time delay for motor applications. But a non-time delay fuse, you can get up to 300%, or should size it at 300%. So as you can see, in most cases, you don't have to go that high. Typically on a motor load, you know, I can certainly size at 150% for class J and RK1 and RK5 and not have a problem with any kind of nuisance trip. But these are basically the maximum nominal ratings you can use for motor protection. When we're talking about circuit breakers, once again, these are the maximum ratings you can use depending on which one. So if you've got inverse time, if you go to that one, you go over, you have 250%. Instantaneous trip is at 800%. And then when you have a manual self-protected, you're going to size it at 100%. So just know when you're looking at these devices, this is how you basically size them. So it's not terribly difficult, but the one thing you will need to know, and that's where if you look in table 50.1 of the supplement, you'll see that they give you these charts in there. So these are the full load motor running currents that are out there. So they have this chart available to you. So in this particular case, if I just pick out a 30 horsepower motor, I go across to the 3-phase 480 volt application. You'll see that I have the red box highlighted there. So at 30 horsepower, that motor is going to draw roughly 40 amps. So that's what it typically would draw, is 40 amps. So if I go back to my calculations, not terribly difficult calculations, but there's one little caveat I just want to talk about. When we look at, you know, in this example, a 30 horsepower, 460 volt controller and contactor and overload, we have, you know, first step, is it controlled by a VFD? In this particular case, it's no. We're going to have a contactor and overload. But if it is yes for some reason, and you are using a VFD, you want to now look at the VFD manufacturer's instructions. So under 31.3.2, the individual manufacturer of that VFD will typically spell out what they want their overcurrent protective device to be. So be on the lookout for that. Take a look at your VFD manufacturer, see what they recommend, and use that. If it's a contactor and overload, we use the tables that we previously described. So now at the 30 horsepower, 460 volts, my full load current is 40 amps. Under table 31.1, if I'm using a breaker, I'm going to take the 40 amps times 250%. I use a 100 amp breaker. If I'm using a non-time delay or a class CC, I can use up to 300%. So now I've got 40 amps times 300%. That gives me 120 amp fuse. And then finally, if I'm using a dual element time delay fuse up to 175%, so now all of a sudden I can take I can have 40 times 175 as a 70 amp fuse. So the nice thing is when you use a dual element time delay fuse, typically you're going to be using a lot smaller disconnect as well, right? So the reason we want to get away from those non-time delay is, one, they're not as good of a device. You can size closer. Class CC are still very good, obviously. They're very small, so that you're not going to really gain anything there because they're already small. But when you're using a dual element time delay fuse, you typically could put in a smaller fusible disconnect switch at that point. So kind of the important thing that I also like to point out is you notice under the non-time delay or class CC fuse, it'll say, you know, it has 120 amps, and then next to it, it says 125 amps next to it in parentheses. That's because under 31.3.7, it permits for the next standard size device permitted. So if we go to that, and I'll show you here real quick. So under 31.3.7, since it permits the next standard size, just know that in the NEC and in UL, there are standard ampere ratings for fuses and inverse time circuit breakers. So the standard sizes, I didn't list them all on here, but you can certainly see that standard size breakers are 15 amp, 20 amp, 25, 30, 35, and this goes with fuses as well. Additional size fuses are 1, 3, 6, and 10. So people have been around for a while or been using fuses for a while. You obviously know that we have a lot of in-between sizes that aren't shown on as a standard ampere rating. You know, we have a lot of class CC fuses that might be even RK1 fuses and RK5 fuses. We might have 8 amp rating or 7.5 amp rating or 12 amp rating. So we have different ratings. So when you do your calculations on this previous slide and it comes out to something different than what's a standard rating, you can go to the next standard rating above that. So you can actually jump up a little bit. So let's say if it comes out to an 11, your rating, well, we don't make it 11. We can jump up to a 15 at that point because that's the next standard size rating, right? So now we can jump up to the next standard size. So just be aware what that says. All right.
There's a question, Matt.
Sure.
Someone's asking if I need to protect the solenoid valve outside of the control panel, what options do I have?
You can use, so a solenoid valve outside if it's coming from inside the panel, you can use it as part of the control circuit if it's coming off the transformer, because technically a solenoid is part of the control circuit. So you're really just activating a coil, and if it's coming from your panel, you would use all the rules associated with your short circuit current ratings. So if it's coming off of a transformer, you can use those rules. If everything's outside the panel, meaning it's getting power outside the panel, then that's a different story. But if it's being activated from the control circuit within inside of your panel, it comes from the rules associated with supplement SB. So you could take, in many cases, you can take the primary overcurrent device on that transformer and rate it that way. So if we look at other sections within section 31, you've got branch circuit protection for motor groups, receptacles, heater loads, appliance loads, lighting loads. So that's all covered in section 31. So if we just kind of look at feeders, look at feeders in these applications, what can be used in feeding applications. So when we look at overcurrent protective device sizing, so when we look at it under 32.3.1a, it says the rating of the largest branched circuit protective device in the circuit plus 125% of all heater loads plus the full load currents of all other motors or other loads in the group that could be in operation at the same time, or the ampacity of the conductors or bus bars on the load side of the overcurrent protective device. So these are the two things that have to be taken into consideration when you're sizing your overcurrent protective device for your feeder application. So a couple things I want to make sure you're aware of. Those two devices on the bottom of this cannot be used in feeder applications. We went through that before. I cannot use that UL508 disconnect. I cannot use that MMP in there as well. Even though I could use that in many cases on branch applications, I cannot use it in feeder circuits. So just be aware they cannot be used in your feeder applications. They must be UL98 if it's a disconnect, or 489 device if it's a circuit breaker. So a manual motor controller and a combination motor controller that complies with the standard for industrial control equipment shall not be located in the feeder circuit. So I kind of spelled it out, but they cannot be used in that feeder circuit. So just be aware. So if we look at how to size this, I'm going to kind of take you through a quick little example of this. So what size should feeder fuse be if it feeds the following? I've got a 125 amp circuit breaker protecting a 100 amp motor. I've got two 30 amp fuses protecting a 20 amp motor. I've got I got four 2 amp fuses protecting a 1.5 amp motor. And then finally a 5 amp circuit breaker protecting a 5 amp lighting contactor. So if we go through our rules for this that we just came across, so we have our largest overcurrent protective device, plus 100% of other motor loads, plus 100% of other loads. We did not have any heaters in there. Otherwise, if we had heaters, we'd add 125% of the heater load. But in this particular case, we don't have that. So in this case, we have our 125 amp branch device. We have our motor loads that were 20 amp. We have two of those. We've got four of them that were at 1.5 amps. And we finally have our lighting contactor that was a 5 amp application. So when we come up to this, we're going to pull out 175 amp fuse. All right, so it shall not exceed that value. All right.
We have another question.
Sure.
In a branch with a capacitor, I know we don't analyze the capacitor, but what about the contactor and the circuit breaker?
They will be part of that. They will be part of that analysis if it's carrying that current. You know what? So it's just, I like to see that drawn out actually. So it's a breaker. If it's a breaker contactor feeding that capacitor, you know, I want to think about that one a little bit. I don't want to give you false information about that, but I'm guessing that because it's in there, it would have to be part of it, but the capacitor itself would not be part of the circuit. But I want to verify that, guys. I'm not 100% sure. Sorry about that. All right, or in this particular case, or the ampacity of a load side conductor. So we want to take whatever the value is we need based on either the loads or the actual ampacity of the conductors. So a couple of things I want to point out from Bussmann. The nice thing is we came out with new fusible disconnects several years ago. We have our second generation of our class CCP. So these are basically the best fusible disconnects on the market nowadays, guys, up to 200 amps. So we do have them through the door disconnects. We have flange mounted. They have lockout tagouts. If you have not seen our Cube Fuse products, please talk to me at some point. They're very nice products. They're the same electrical characteristics as a Class J. They've been around for over 20 years. If you're a panel builder and you want to save space, it's definitely a place to save space. We do have them so that you can mount them in a fuse holder, but in this particular case, because they're a small, compact design, we introduced fusible disconnects for these a few years ago, and we came out with our second generation about 2 years ago. So the nice thing is with the second generation, we have through the door disconnects, we have better lockout tagout mechanisms, still a small size, and now we go up to 200 amps. And eventually, I hear through the grapevine, we should have our 400 amp here launched by the end of this year. Hopefully, actually September timeframe. I heard third quarter. So just know that it's a nice product. When you look at the smaller size of it, when we're talking about a Class CC version, it's about 43% smaller. On our up to 100 amps, we're about 50% smaller. And finally, when we go up to 200 amps, we're potentially 69% smaller than a typical 200 amp Class J fusible disconnect. So they're nice devices. On the 200 amps, they're a little more modular, meaning we can add through the door disconnects and we can add side disconnects. And if you want to, on all three of these cases, you could just have them inside of your panel. So maybe if you want to have you have multiple drives in your panel or some large contactors, and maybe at some point you want to isolate them, you can have a disconnect inside. So that's a toggle disconnect that we can utilize, and that is all available now.
We have another question.
Sure.
So it's on the previous example. It says, can we go down to 175A instead of going up to the next size up when calculation comes in at 176?
You could go down to 175, sure. It's just said the feeder fuse shall not exceed. So in this case, on the motor case I gave you a little while ago, we were able to use a next size larger, but in this case, it says a feeder fuse shall not exceed. So once you calculate it, we now had to go kind of drop back a little bit to a 175 amp fuse. So yes. All right. And these are obviously some of the options that we have typical out in the marketplace. But the nice thing is we got through the door disconnects, flange mounted disconnects for these devices. And it's a nice item out there for your panels. And once again, it's a lot smaller, a lot more compact. And even if you decide, you don't want to use a disconnect version, our fuse holders themselves, guys, if you look at a 100 amp Class J finger safe fuse holder, our 100 amp Class CF, which is a cube fuse, is probably half the size. And dollar for dollar, it's actually less expensive to put a system together with a cube fuse because it is all finger touch safe. So, and it is a lot smaller as well footprint. So I encourage you strongly to look at it if you haven't already. We're talking about surge protection devices. So if you are putting in a surge protection device, please make sure that it does adhere to UL508A. So under 47.1.1, when you're using a surge device, you must adhere to that criteria. So if you're looking at NEC requirements, if on many industrial machinery now, so if you're doing anything industrial machinery related, safety interlocks have to have surge protection on them. So you want to make sure that if you have any kind of safety interlock circuits, they have to have surge. They want to make sure that any kind of surge doesn't wipe those things out. So just make sure that if you're doing any kind of machine application, industrial machinery, or putting enclosed stuff on the side of there and you're controlling the safety interlocks, you have to have surge on those. So just be aware of that requirement under NEC 670.6. So we're talking about branch size ratings for other devices. So we're talking about 31.5. So when we look at, like, if you got a duplex receptacle, for example, basically what you're going to do is match your branch circuit protection device to your receptacle. So if I've got a 15 amp receptacle, I can put a 15 amp branch in there. When we're talking about heater loads, we really want to try to limit the heater loads to less than 60 amps. However, there are exceptions for that. So they would encourage you to break up those amp ratings on your heaters. But obviously, I've been involved over the years with some large heating applications, and sometimes it's not possible. But there are exceptions for that as well. So you do want to look at 31.6 to understand how to size those. As far as appliance loads goes, most of the time it's by the manufacturer. So what does the manufacturer recommend? Use their recommended. If they don't have recommended or they're not marked. So for appliances less than 13.3 amps, you're going to use a 20 amp branch. Anything greater than that, you're going to size it 150%. So pretty straightforward there. And then lighting loads, 20 amp max for standard duty, but there are some heavy duty marked equipment out there, but it has to be marked that way. And you can get up to a 50 amp max if you have to. So it's under 31.8. So pretty straightforward. I touched on this a little bit yesterday when I talked about devices that go inside of your control panel. I just want to make sure that you're aware of them. So under 26.1.1, a fan, air conditioner, heater mounted to the industrial control panel for the purpose of conditioning air within the control panel shall comply with requirements for general construction and power circuits in addition to the requirements for 26.2. So there's a big exception there, though, guys, and this is the big exception. A fan that complies with 26.2.1 and a heater that complies with 26.4.1 are able to be supplied from an isolated secondary of a control transformer and comply with the requirements for control circuits. So what that means is if I have a fan or a heater, I want to make sure that I can come off the secondary of that control transformer if possible, and then all of a sudden I can now take into consideration the rules for a control transformer, and I can possibly use the primary overcurrent protective device of that control transformer to rate that whole circuit. So that basically takes the SCCR rating of that heater and that fan out of play. So certainly if you can do that, do that. If you can't, then you have to adhere to 26.1.1. Air conditioners, however, are always part of power circuits. So just when you're looking at your SCCR ratings of it, if you have to put an air conditioner on, find out what their SCCR ratings are. Use any of the manufacturer's recommendations to possibly raise that, but they are part of the power circuits. All right. Control circuits, lighting, and maintenance. So if you have to put a light in for maintenance purposes, the maintenance lighting circuit shall comply with the requirements for a power circuit in sections 28.6. However, once again, there are exceptions. As long as you're coming off that isolated secondary of a control transformer and comply with the requirements for control circuits, it can all be part of that control circuit. So there's if you do have a light inside your cabinet, which is pretty common, obviously, in larger enclosures that you see here on the right, you can comply using using the rules for a control transformer. Once again, if you can meet that requirement under that exception, and then you can use that overcurrent protective device on the primary of the control transformer to help dictate the SCCR rating of that branch. And then also number 2, LED luminaires are able to comply with requirements for those control circuits as well. So they fall under exception number 2. So when we talk about how do we size up overcurrent protective devices for transformers, this is a nice little section I wanted to put in here so you're aware. So this has to do with primary winding only, or sizing overcurrent protection on the primary only. So we're looking at control transformers or smaller transformers on primary only. It's basically going to be sized at 167% in many cases. So in this particular case that we have on screen here, I've got a 3000 amp rated control transformer. I've got a 480 primary, 120 volt secondary. So in this particular case, I have 3000 amps. If you look over to the right, I have my overcurrent protection device calculations. So I have my primary, which is 3000, which is a 3000 VA transformer divided by the voltage on the primary, which is 480 volts. That's 6.25 amps. I multiply that by the 167% up top from the chart, because in this particular case, once again, it is a transformer whose current is between 2 and 8.99 amps. So that's how we get the 167%. So when we did our calculation, that's the primary current rating. So now we can size this at 167%. So in this case, we have 10.44 amps, and we can, and we do a 10 amp FNQR fuse on that device. If we're sizing for primary and secondary branch circuit protection, now we have a couple of rules in here, right? So on the primary side, we want to look at that same 3000 VA transformer. If we look at what we have now, we can actually size a little bit different, because now we have primary and secondary protection. So on the primary side, we look at the chart again. Once we do our calculations and we come out with the fact that it's 6.25 on the primary, we go to that column that says, all right, between 2 and 8.99 amps, I can now size my primary branch circuit protection at 250%. So now I can rate those fuses at 16.25, and now I can bump it up to our standard size, which is 20. So now I can jump up in size because I now have secondary protection as well. So on the secondary, when I go up to the chart, well, once again, I got to do calculations. I got to figure out that, okay, I got a 3000 amp. Now my secondary, I've got 120 volts. So 3000 divided by 120 is 25 amps times 125%. Because now when you go up to the column, you'll see that 9 or more amps, I now size it at 125%. So now I put in a fuse that is rated at 35 amps, because that's a next standard size out there. So when you're talking about primary and secondary overcurrent protection, you can size a little bit higher, and maybe that's the case because there are times out there that I've certainly seen where control transformers in particular are getting more and more efficient. You may see more and more current go through those as they fire up. So sometimes you may see a nuisance trip. So basically what you want to get is the most current limiting class CC fuse out there, which is our FNQ series, FNQR. So when you put that on the primary, it gives you the most time delay, and if you put a secondary protection, you can maybe put some larger fuses on that primary. Hopefully that makes sense. Pretty straightforward. So some other topics to study. A couple things I want to make sure you're aware is what your nameplates have to look like. So when you look at 52.1, an industrial control panel shall be provided with a nameplate marking that includes the following. So you got to put your name on it. You got to complete electrical rating of each source of supply. So you want to put your voltage ratings and other device things on there. Your short circuit current rating, field wiring diagram. You want to put any kind of factory identification, and you want to put the enclosure type on this panel. So under 52.1, this is what you have to rate. So if you look at an example labeling of a panel, we have our serial number, we've got the voltage, we've got the phase and frequency, we've got the current. We have to list the largest horsepower if there's motors in there, so that's the largest horsepower. We want to list the SCCR rating. In this particular case, it's 100,000 amps. Overcurrent protection provided at supply terminal, so it's inside the panel. We have an enclosure type rating of type 1. And then finally, we have our diagram ratings. So, and then the name of the tool itself, of the company itself. So this is everything you would need to label on a panel. And please pay attention to this because you don't want stupid little mistakes to happen. You know, there's one panel that had a dumb little mistake. You know, they put the manufacturer's name, they put where it goes, the serial number, the voltage, the full load current, the horsepower rating, but their KVA, they listed KVA as the fault current. Well, that's not really a fault current. It should be 5 KA. So you just want to make sure that little things out there. So KVA has to do with transformers, but you know, we're talking about KA, which is how many amps it can handle. So in this case, you want to make sure that it's accurate. You know, they have their diagram number on there. They got their NEMA type number on there. So just make sure you have all the information that you need on your panels and label them properly. And a couple of reminders from yesterday. When we look at what had to be labeled from yesterday, if you do have high fault current ratings in there, you must label it that way as well. So if you are using high fault current ratings, you must put this warning label on there that says the opening of a branch circuit protective device may be an indication that a fault current has been interrupted. All current carrying parts and other components protected by this device should be examined and replaced if damaged. So you do want to put this on there as well. You will need to do that under the labeling process. When we look at another example is when we have an external device. So if I've decided to leave it up to my customer, or I've actually said, you know what, my customer asked me not to put in the main overcurrent protective device, I now have to list that on the panel. So under SB 5.1.2, if it's a branch circuit that's coming from elsewhere, you have to label that. And under SB 5.1.3, if it's a feeder circuit being protected from somewhere in the field, that also has to be labeled. So you'll see on this particular label that I created at the very bottom right, you'll see SCCR symmetrical is 65K when fed by 200 amp class J fuse. So you have to put that you'll get that, but it has to be fed by a 200 amp class J. Doesn't say ours, just because what happens is when they did their study, they used the tables provided by UL, and they said, all right, I'm using the rules supplied, and I'm just going to spell out must be a class J fuse. It could be a case where you must spell out, it might be so granular that you spell out a particular breaker. So if there's a particular current limiting breaker that has been spelled out to use in the feeder, you might have to spell out an exact part number in this particular case. So just be aware of that. All right. It must be labeled if it's coming from a separate source. So why would you want to have an external disconnect? You know, obviously potential cost savings to panel builder. So if you guys are building a panel and you don't have to put it in, it could save you some money, right? It could also decrease the panel size. So if you have a small footprint you're trying to adhere to, you could say, you know what, I might only have so much room here, but I've got a little room right next to it that I could put a disconnect switch in. Okay, I can decrease the panel size that way. But a really good reason to do it is to increase safety to the installation and maintenance crew. So some things you may have never thought about. If I can put my disconnect just external and just ahead of the device, and I put in, let's say, our 200 amp class J, in many cases, I'm going to drastically reduce the incident energy available. So if I'm all of a sudden have to, for some reason, I get permission to work on that panel live, the fault current and the overcurrent device protected by my fusible disconnect upstream, class J, 200 amps and less, because many enclosed systems, industrial control panels, many of them fall into 200 amps and less. And when that happens, this is a chart that I pulled out of our Slightly Protected Devices Handbook. So that's another piece of literature I'm going to show you at the end of this, just to kind of go on our website and grab it. But if you look at this chart, what it's saying is that on the top, you'll see 101 to 200 amp, and these are low peak products from Bussmann. So if you use our low peak products, we will get an incident energy level shown there depending on the fault current. So if I go over, for example, over to bolted fault current of 10,000 amps, right in the middle, I go to bolted fault current, go down to 10, go across, my incident energy level is going to be very low. It's 0.25, which is very, very, very low. And my arc flash boundary is very, very, very low as well. So if you can put it external, it's great. The reason it's a big deal is because if it's internal to the panel, the line side of that is still a very high hazard risk category. So the line side terminals, if it's inside of your enclosed cabinet, still see the full available fault current. They're not going to get the benefit of that overcurrent device. They're not going to get the benefit of that if your disconnect switch, your fusible disconnect switch, is inside of that panel, because you still have power to the line side of that. The other advantages, obviously, is once you turn it off, and if it is external, if your disconnect switch is external to your enclosed cabinet, once you turn it off and you go into your own cabinet that you've manufactured and you've labeled and listed, that now, once you test for absence of power, there's going to be no power whatsoever in there, right? Because you've now turned it off. There's nothing even on the line side of that panel. So a couple of really good reasons. One, if you do have to work on it live, for whatever reason, you're going to have the benefit of a very good current limiting fuse above it, especially if it's a Class J fuse, which is very common. And two, you're going to limit, your exposure if it is inside, if you do happen to put it inside the cabinet. So very good reasons to put it external to the cabinet. I strongly encourage to do so. So when we look at supply voltages, we want to make sure that our supply voltages are properly labeled and marked. If it is a slash rated system, you want to verify and know that it's a slash rated system. You just can't put 480 on it. You must put 480Y/277. So you do truly have to understand. So under 54.2 below, it says for an industrial control panel with a slash rating, as in 49.6, the input terminal shall be marked for use on a solidly grounded Y source only or equivalent. So just know that it must be labeled that way, and you must understand what voltage you have coming into your panel. Appendix A and B. Appendix A is all the component standards that can be used in industrial control panels. So if you want to flip through that, it talks about all the different standards. And then Appendix B are unevaluated components. What do you do if you got some components in there that just haven't been looked at, but they're inside of a control circuit? I've never spent much time on this, but I want to make sure that you know it is available, and you can skim through that, take a look at that. So this is a biggie because in Pennsylvania we haven't adopted this yet, but I do want to make sure that you're all aware of this before we head out, before we finish up for the day. Under NEC 409.22, it has always been the case that you shall mark, under 409.110, which is down at the bottom, an industrial control panel shall be marked with its SCCR. So this is what you guys have been doing for a long time. It's been in play since the early 2000s, where you had to label your panel with the SCCR. So 409.22, all of a sudden now an industrial control panel shall not be installed where the available fault current exceeds its SCCR. So now all of a sudden it says in 409.22, it says, you know what, you can't install it anywhere where my available fault current is greater. So the gentleman at the beginning of this conversation says, what happens if I don't want to, raise the rating? What if I don't want to use a high fault? Well, now, if your panel is rated at 5,000 amps and you list it at 5,000 amps, it cannot be installed if all of a sudden whoever calculates it says, I can't install that because I have 15,000 amps available. So I can't put it in here. So 409.22b takes it a step further in NEC 2017. So 409.22 showed up earlier, I think in 2014, but 409.22b came into play for the National Electric Code in 2017. And that basically now says you have to calculate, date, and document what your available fault current is when you go to install your equipment. So very different, guys. So it used to be that you just put your SCCR ratings on and kind of walked away and kind of left it up to the owner. Now it has to be the case where when it goes in, you have to calculate, date, and document what the available fault current is. So it's a big change, guys, to where we've come from. So I think probably what happens is a lot of authorities having jurisdiction, or a lot of inspectors, or whoever, or just noticed over time, yeah, it's great that they're saying what their SCCR rating is, but it really doesn't meet what we need it to meet. And quite frankly, guys, I get calls a half a dozen times a year at least where equipment goes out into the field, and that's the problem, right? They want to put something in as a 5K rating, but they've got 20K available. What do they do? And then there's only so many options in that case. So just a quick success story in this case, we had a customer called Strasbourg. So just to kind of take you through real fast, they went through this, and this is real life stuff where they had a panel, and I'm kind of going to go through this fast, I think, because we got 15 minutes. So if we look at their particular situation, they had two different panels on their equipment. So in panel A, they had, 60 amp circuit breaker. It was 65,000 amp interrupting rating. They had a 65 amp contactor. The default was 5 kA, but it was 65K with a 100 amp breaker. So in this particular case, because they did everything right in the panel at the top right, they were able to raise the rating of that contact, or they had a combination rating, let's say, with that contactor. So because the contactor is less than 100 amps, they were able to meet it. So their panel rating on the top panel was 65 Ka. The problem is on the panel downstream, they actually had a very low rating. So when they looked at what they had, they started doing an analysis on it, and they realized, well, I have a rating of 65, but you know what? It's not good for my customers out in the field. I got some pretty heavy duty equipment going in here. Certainly, we got more than 5,000 amps available. So, we need to analyze this. So they analyzed it, and they said, panel B contains some servo drives that only have a 5K rating, and we've got some miniature circuit breakers in there. They only have a 10K rating. There's no current limiting devices upstream. What can we do to correct this? What can we do in this particular case? So what they did and what we helped them do is basically say, all right, if you want to take it up a little bit, we can actually look at those drives, and those drives with a 35 amp fuse can get an 18 Ka rating on them automatically. So just by basically switching out those miniature circuit breakers with our compact circuit protectors with some Class CC fuses or some Class J fuses, or Class CF, sorry, we can help get those ratings up to 18,000 amps. And that's specified by the manufacturer, right? We're not using those branches to raise the ratings. These are already tested values from the servo manufacturer. They have a default rating at 5 Ka, but then they get an 18 Ka rating with a max 35 amp fuse. So we're following the manufacturer's instructions. However, what we saw out in the field, or what they saw, is that, hey, we need to figure out a way to raise this all up to 65 Ka, because there are times out there where we need to get to 65 Ka. So a couple things that they can do, they can now take into consideration the feeder device. So the nice thing is, in their case, they're able to get to higher ratings, specifically 200,000 amp ratings, with breakers and with fuses in this case. So I'm sorry, on panel B, they can get to 200,000 amp rating. So when we look at what we have, if we replace the top right with an LPJ Class J fuse, it's a current limiting fuse, that's 100,000 amp rating. We can get with that contactor and the fuse combination that's there, they have 100,000 amp rating. So we can get 100,000 amp rating on that panel up on the top right. And then when we look at all the let-through currents of that fuse now, by using the let-through currents and the rules that are in place for taking the feeder circuit, we can now apply that to the SCCR ratings of those servo motors downstream, those servo controllers downstream, I should say. So now all of a sudden, if we look at that, we can say, all right, we can get a higher rating on panel B by utilizing the let-through currents. So with a Class J fuse, we're able to get up to 200,000 amps on Class B, on that panel B. But even still, as they investigated it, they were able to use a current limiting circuit breaker in this case as well, and to be able to get a higher rating as well. So just know that there's real life examples out there to be able to use and simplify it and make sure that they can get a higher rating. So, and this is nice. This is a nice situation too, because once again, they could do some troubleshooting. Now, if they put I would certainly recommend putting in a Class J fuse, because when you look at the arc fault, I'm very sure that it's going to be less than what it would be if there's a breaker there. So just know it's not 100%, because I haven't done the calculations. But when you're talking arc flash protection and that kind of stuff, when you have a Class J 60 amp, it's very, very good for arc flash protection. So
Here's a question, Matt.
Yeah, sure.
Someone's asking, how about field changes at the control panel? For example, adding extra inputs to a PLC or an extra motor starter.
Extra motor starter will be a problem, because now it's part of the control circuit that have to be reevaluated, but extra inputs to a PLC is part of the control circuit, so that won't be a problem. So if it's part of the power circuit, it'll have to be reevaluated again. So if we look at additional resources and tools, we have a nice handbook that's available for 2017, SCCR code change booklet. Busman has a nice app. I encourage you to go out there and grab this app off of, if you're Android or Apple device, just look up fault current calculator, and what it does, it helps you calculate the fault current. So if your customer doesn't know what they need a design to, or if you're helping them come up with a design situation, this calculator is very easy to use. It'll help you at least establish what your baseline is. If you're going to install something at their facility, you can give them this tool and they can figure out, yep, you know what, I have 22,000 amps available. And the nice thing is with that tool, you can also use that to print a label to send to yourself, so that to comply under the new NEC rules of 409.22, you can now all of a sudden say, hey, I comply. Here's when I calculated the fault current. It's 22,000 amps. I designed my enclosed control panel to be 65,000 amps, so we are in compliance. So it's a really nice tool. You can actually email yourself a PDF that will create a label for you, and you can print out yourselves. So we have a Fusology handbook. We have our selecting protected devices handbook. We do have an SCCR protection suite. A software package we introduced a few years ago called Oscar, we just recently retooled. So when you look at Oscar, it's basically an online short circuit current calculator. So it does help you evaluate your circuits. We did redesign it in the past couple of years. We relaunched it just not long ago, within the past month or two. So quite frankly, I'm still tooling around with the new design, but it's a nice way to come up with a short circuit current rating for your cabinets, especially if you have customers in particular who want to understand the methods you use to calculate your short circuit current ratings. I've seen some cases where some big industrials out there want to understand what method you use and how you came up with it. Well, with Oscar software, it prints out a little report on how it came up with the values. So that helps you to come up with that in case you need more of a definitive answer for a customer you're trying to hook. All right. And we can give you a free trial if you use a rewards code.
We have another question.
Sure.
Are UL 1953 power distributions good for feeder circuits always? The standard mandates the spacing listed in table 10.2.
Yes, UL 1953 meets the requirement for the spacing. They're designed for feeder circuits. So last couple of slides, obviously UL training courses are free up until August 1st. There's 12 modules on there. I recommend that you go to UL Product IQ. You can create your own login. So if you do have to look up some of the information on some of the listed products and recognized products that I showed you before, especially one regarding UL 1953 and 1059 products. And you know, you want to mess around a little bit, know how to search for products in there, know how it works. It's not the most user friendly, but you definitely want to be able to chug through it if you can. Complete the exam by August 1st. Once again, have to complete it 1 4-hour sitting. It's open book, 2 attempts to complete, and required UL training, you know, will be required if you don't pass in the first 2 tries. So I good luck, everybody. I hope I helped in some way the past 2 days. Obviously, there's a lot to learn. I only touched on a portion of what's in the UL standard, but I'm hoping that at least gave you some good information. I appreciate it.